See where the level is now? That's where it was. That's not because the cork soaked that all up. So it's down a little over a millimeter. What's the point here? The point here is that when dealing with homogeneous mixtures, solutions, you can't just add up the volumes of the molar species and get the volume. Well, is that a problem? I guess not for most of us. Unless you're mixing drinks in a bar. But it is important because volume is just one extrinsic state variable. You've got to mix. What are some others? Energy, enthalpy, heat capacity. Three energies we'll be talking about. Entropy we'll be talking about. And they all work the same way. You can't just write the energy of a solution as a sum of the energies of its components. Unless it's a very special solution, and there are cases where you can, but generally you cannot. And the three energies in the Gibbs function, you can't just say that it's a sum of the three energies of its components. They are not. So we have to have a way to deal with this. Does that make sense? Just saying one demonstration should convince you that there's a need for something more than this equation. I would V I squared and the answer is generally not. Generally not. So what do we do about that? First, that's just an observation. That's the way our environment behaves. So now let's talk about interpreting that. We've had some good experience interpreting things, getting this far. So someone tell me why the volumes don't add up. Yes.
They fill the spaces in between bonds.
In between what?
In between, like, their structure. So, like, the ethanol can fit between the water molecules.
You think the water molecule changes?
No. I'm saying the ethanol can fit between the water molecule structure.
Well, it's a bigger molecule than water. I don't know. Maybe, but that's not big.
I think there's a invisible attraction between the two. There's like a certain invisible attraction between the two components.
Yeah, but why?
Well, they're invisible.
Are they invisible? But they're invisible. All right, well, we know why. We understand why. Okay, so let's consider a pure liquid. Here it is. And it has molecules, and I'll draw them little circles, greatly magnified. Now, why is this a liquid and not a gas? Why do liquids exist? What is absolutely essential in our view of the nature of matter for liquids to have an existence?
Attractive forces.
That's right. There have to be cohesive forces between. Are there cohesive forces between molecules? Oh yeah, we've argued that right along. All molecules attract one another. They may repel as well, but there always is some level of attraction. So they exist in this state because of cohesive forces. Now, if that's water, for example, pure water, from zero, say pure here in this case, is about 18 cubic centimeters per mole. So what's the volume that a water molecule occupies on average in water distillation? It's just that number divided by the Cox number, right? It's itty bitty to it. And they say, well, the water molecule has to fit in a volume about that size, and you assume it's a cube or a sphere or whatever, and figure out what will fit inside. It turns out to be three or so angstroms across, which is about what we think. That's right. So this is equal to Avogadro's number times, now if I move V, with 0 on it. So this is the molar volume, and this is the molecular volume. If you like, it's the share of the volume that that molecule commands on average. So move. And then we take that molecule and put it in for B. Now this has different kinds of molecules, so I draw them little triangles. Here are the cohesive forces. Hold it together. I'll write F, A. Interactions between likes. Here are the cohesive forces. I represent those F, V, B forces. Are these the same in general? No, they're not. Each liquid has its own affinity for its own kind. They're generally different. Now, I take this water up here that I had a minute ago and slop in one of these things. Oh, by the way,
Can you slide it up?
pardon?
Scroll.
Yep.
Is that right?
Yep.
Mole volume V is equal to N times V Lumen. And so this is the molecular volume. Not volume of molecule, volume of the liquid that the molecule commands. It's attracted to its neighbors, it's also pushing on it, but they're bumping in on it. So now we put this interloper in here. So volume of B now, and I put a 0 on that, because that's in the 0. So volume of B now is no longer what it was. Does this make sense? Why? Because now we have an interaction F, A, B, which is different than F, B, B. So if we go and make a solution out of this now, so we've got a bunch of these, a bunch of the others. We have these forces. There's also some FAAs, there's also some FBBs. And so the cohesive forces are very good. All right. Just common sense. If the molecules in if the dissimilar molecules have more affinity for one another than they do for their own kind, if you put them in this strange new environment, they say, oh, that feels good. And then what? They cuddle up closer and they command lesser volume than they did in a pure current. And the volume of the mixture is less than the sum of the pure volume. If, on the other hand, the cohesive or the force between dissimilar molecules is less than the cohesive force between in their pure phases, then they're not quite as comfortable. They're still coherent, they're still part of the solution, but they aren't quite as comfortable. They don't like their neighbors on the average quite as much, and so they push them back and they command more volume, and the volume goes up. Now this is not one molecule getting in another molecule or pushing it away. It just how much volume can an individual molecule say, this is my space, give me my space. On average. It depends on how it interacts with its neighbors. If by chance it can't tell the difference, you put it in this foreign environment and it says, oh, this feels cozy this side, very similar to coziness I had for this fluid. Then there's no change. But that's a pretty special circumstance. We'll talk about some cases where that's approximately fulfilled. So if that makes sense, then we can take this next step. The volume of the solution is generally not the sum of the molar volumes of the pure thing, but equal sum of Ni times the volume. I put a bar over this now. So define I have a bar over it as the molar volume that species commands in that mixture. So it's not the full volume, it's just a part of the volume, it's called the partial molar volume. And it is equal to change in volume of the solution, which is V, with respect to the number of moles of species I, when we're not changing the pressure and the temperature, and all the other molecules in J's, where J is not I, are constant. It's a partial derivative. It is another state variable. It's an implicit state variable. All right. So this is the definition of partial volume for any extensive state variable. Fi is equal to partial molar F constant pressure, constant temperature, and I just write TPN, means all the other molar numbers are fixed, not changing, just changing I. Does that make sense? For pure material, we have the volume is equal to N times molar volume of pure stuff, and the partial of volume respective N at constant pressure and temperature is just equal to the molar volume. So if you swap some more water in some water, the volume goes up, and it just goes up in proportion to the number of moles you put. There's no shrinkage or expansion due to different compatibilities of the molecules having to share the environment. Okay, so this is an important definition: partial molar volume, partial molar extensive variable of any kind, partial molar energy, partial molar enthalpy, partial molar heat capacity, partial molar fire. So this is what we expect. Use the volume as our sample extensive state variable. found this by process of intuition. We just reason it out. It'd be nice if we had more scientific, more mathematical based reason to believe this. So, maybe more elegant, but I'd say mathematical. Derivation of this formula. So that means we digress briefly for a short format. Okay. Multivariable function f of x is equal to f of x1, x2, xn of n variables on all x's to be in is said to be homogeneous of degree alpha. And you said if f you multiply each variable by some constant called lambda. If this is equal to lambda to the alpha power times x. So that's a definition of homogeneity of mathematical multivariable function. And it's pretty easy to see that extensive state variables are homogeneous of degree 1. Suppose it's the raw volume again. Suppose these are all volumes. Volume compound 1, volume compound 2, volume compound 3. Make up a solution. And then if you double the number of moles of each of them, made up a solution that has the same composition, but just more of it, you would double the volume, right? So if you multiply each of these by 2, you multiply the initial volume by 2, lambda to alpha is 1. So homogeneous state variables are, so the extensive state variables are homogeneous at degree 1. And you can easily show that intensive state variables are homogeneous at degree 0. So we're interested in the extensive ones here right now. Then we come to the part we want to review. It's proven back in the early 19th century by a famous mathematician named Quayle. Hume's theorem on homogeneous functions. And it goes like this. If f of x, as I defined before, is homogeneous of degree alpha, then stop here and we just prove this. I know you don't want to see that, nobody ever does. So prove, see, posted. Next. So we've seen it proved, now we will apply it to a sensitive variable. That says, let's say volume for a second. That says that the volume times 1 is equal to the summation of partial derivative of xi. Then I need to split it right out here. Pure volume is equal to a function of the pressure, the temperature, N1, N2, and put that in. So why it's homogeneous of state 1 but only the mole numbers. So we have to keep the pressure constant, the temperature constant, and all the other M's constant, and multiply it by x. Well, that's just V1. I mean, that's N1, those are mole numbers.
So what is that?
But F equal V, partial V, expected, and that's still N. I'm not practicing corrupt. It's by definition partial or volume. So we get the volume of mixture is equal to the summation of 10I pi bar. That's what we intuited, which you get right out of mathematics.
Could you scroll it down?
So that means we're free to go ahead and use that in our thermodynamics, and we will do that. Put that to rest and get on with the exciting world of thermal chemistry. First off, thermodynamics at its very best. I said that proof would be there, and it will. So here's the first page of it. Just a couple pages. Also, I pulled this out of our textbook. So every now and then I find something useful in there. This is showing the partial molar volume of water, partial molar volume of ethanol in mixtures over a mole fraction range from 0 to 1. So how in the world will we measure those? We better talk about that briefly. You see, water is 18 cc's per mole, and ethanol about 58. Then you start mixing them together. You've got this little nipple here on water, and then it falls way off down here to about less than 14, and ethanol falls way off down here to about 50 or 52, 58, way off. It's really interesting. So, perhaps we should mention further these things. So back up to say measure sort of a binary solution. No sense making this harder than need be. So, moving on. Then I finish this up on. That looks so big.
Oh, that was really
Yeah, there's a zoom.
Just
Lift it.
No, there's a zoom button. Look at the lens. See how like zoomed in it is?
Seems
Yeah.
to be.
There
There
we
we
go.
go.
Oh, autofocus.
Tell me what's not a good size.
That's good.
Is that right?
Yes. Today the 22nd.
Alright.
No.
So, we were
It's the
talking
12th.
about
Sorry.
expansions of an ideal gas using nitrogen as an example, assuming that it is an ideal gas in these expansions and that there's no vibration excitation, so the thermodynamic properties are actually fixed them out here. We went through this and looked at a reversible isothermal expansion, where the pressure volume product was constant, and a reversible adiabatic expansion, where pressure times volume for the gamma power was constant, and calculated the heat effect, work effect, and change it in energy, energy U, and change it in enthalpy. About those processes.
To you.
And started go back and really the gaps I may have left just at the end of the lecture. Pad 1, I think, we did that out of the problem. Pad 2 was this pad. I showed you how to calculate the temperature change, because this will definitely cool off since the gas is doing work to against the applied pressure, and the energy that it's losing is not being restored by heat flow from the surroundings, so it cools off big time. And we got the change in temperature and the final pressure. So I think I did get through that all right. And then to go continue to calculate the change in energy, the differential is dq pad 2 plus dw2, and say the adiabatic, this term is 0. And rather than horse around and try to integrate the minus pdv, which is perfectly all right, sure, we get the right answer to do it. I just took the shortcut and said, well, we know that the energy of an ideal gas functions on the temperature, so change in energy is function of change in temperature, and its energy is the heat capacity constant volume that we integrate. And so we did that. I don't care how you work problems, as long as they're defensible and like to follow. I just don't like to calculate a lot of things and then put them together and calculate another thing. No. Personally, so I do that. I just do one calculation here rather than calculate the number of moles. I've taught this a time or two in the past, and I can probably count on half a hand of the students just insist on calculating the number of moles because that's comfortable and familiar, so go ahead and do it. How? We did that calculation and found that it loses 735.7 joules of energy on adiabatic expansion. Then we want to calculate delta H. And again, we either need the number of moles or we just say, well, hell, we know that this is in CP delta T, and so if we just take in CV delta T, we know from above and multiply by gamma, we got it. There it is. Does that make sense? That's what I was referring to in the main argument. One way or another, you've got to get this answer. So we've done that, and I just combine all those results on the diagram. We have the path one, there's a heat flow into the system, 842.9 joules. The work done on surroundings is that, the work done on the system is the negative of that. It's just sad that we have to put up with it, and I have to cope with it. Then for path two, we finished that up now. We've seen that the heat effect is zero, it's adiabatic. The work effect we just calculated minus W. I'm calculating here the work done on the surroundings, because that's what this expansion is all about. So the work done is minus 735 joules, and the negative of that is plus 735 joules. And the change in energy, we have is minus 735 joules in CEDP. And the change in enthalpy is in CP delta T, and the final reference. Now, I've done some lovely artwork here and sketched out those two paths and hatched in the work done on the surroundings when the expansion proceed in this direction, their expansions. These are reversible paths. We go back up there too, except for the infinitesimal rotation of the surroundings. But going this direction, work is done on the surroundings. It's minus. Sorry. And so for the isothermal path, this is isothermal, and this is adiabatic. So it's pretty clear. The area under the top curve is the work done by the isothermal process. The area under the lower curve is the work done by the adiabatic process. And the difference in them, which pretty clearly the area between the two. Tricky stuff. Now, what I want to do is consider the third process. Just say nitrogen system. And schedule, you necessarily go through here. I want to just there for the precision. So this was our path one, and this was our path two. And we come up to the same volume here, which was whatever, 4 liters. And now what I want to do is connect this state to that state by, what do we have to do that? What do we have to do to our system? We're in state one, we expanded isothermally. Now we're going to do what? We'll keep the volume constant and change the temperature. Let's lower it. So how do you do that? How do you change the temperature? Usually you connect it to something colder in the surroundings with a heat flow. Right? We do this conversion. We just draw the heat flow by exposing the temperature to slightly cooler and then change that temperature. So this is path 3 going in that direction, and this is isophoric cooling. From T1 to T2 at bottom nuclear. All right. So that path 3 is moles of nitrogen. It's nitrogen. pressure, which is 2.27. And the temperature was 227 K. And we do this across the clock. And whatever written out change in state. Delta Q3 is equal to Q3 plus W3. How much is W3? We can look at that chart, read right off that chart. Bang. It's the area under that path. What's the area under that vertical line here? Equal area. So delta U3 is just Q3. This is the energy of an ideal gas functionally at temperature. That's equal to NCV T. Oh, that's the same thing we saw up there on path 2. We know what that is. It's minus 735. 0.7 joules. Now I want to get delta H3. So that's Q3, and that's delta U3. Delta H3 is just NCV. Delta V, we calculated that just a moment ago too. That's equal to delta H2, and that's equal to minus 1030 joules. Now the reason I wanted to take this third pack is to make them. I want to see what happens. We start here in this state, and we go on an excursion. We come down this reversible oscillating expansion, we cool it up down to the temperature that the adiabatic expansion would reach. And then we turn this one around and run it backwards. We can do that, it's reversible. And run back up to this point. Then we'll have a cycle. I want to see what's conserved in the cycle and what's not conserved. And what's your expectation? How about the energy and the enthalpy? We integrate around that cycle. There's a little integral sign with a little circle on it. What will we get when we integrate any state variable around that closed path? Zero. Thank you. So we'll get Z. We better get zero. And what will we get when we integrate Q and W, dQ and dW around a closed path? Probably not zero. Because they are not state variables. There is no heat. Nothing has any heat. Nothing has any work. There is no delta Q. There is no delta W. Do not have expectations of it. All right. So here it is. We've got a cycle now. Path 1 plus path 3 minus path 2. So now we're going on that cycle as I've drawn it out here. 1, 3, minus 2. And we know all these things. I'll come back and talk about this heat flow and work flow in a moment. We just summarize all those things we can, except we add path 3 to it. So there's what we had for path 1. Here's what we have for path 3. We just calculate those and then they go. Here's what we had for path 2 if you change the signs on everything, because we're going on it backwards. That's all from that previous chart. And then we sum these all up and look at the net. And you add these together and you don't get 0, you get 107.2 joules. That was heat flow to that's heat flow to our ideal gas. And minus work, that's the usual work, that's work done in the surroundings. We got 107.2 joules of work done in the surroundings. What happens when you add up the delta U's, you get 0. Isn't that nice? Now if you efficiency. Why? U and H for state functions. And their differentials are exact. And if you go around the loop and stop where you started, there's no change in that. They can change a while, but they're not on that loop somewhere. But there's no change in that when you get back where you started. Thinking about this, getting comfortable with these ideas makes working problems, including problems on examination, a whole hell lot easier. Any question on that? Well, I told you earlier that the only chance we have, only opportunity we have for converting heat flow, energy component heat flow, into useful work minus W in the surroundings. The only chance we have for doing that on a closed process has to do with the inexactness of dq and dw. So let's look at that cycle here just briefly. And I wrote these things down on here, I'll just refer back to them. So here's our system. It's just into gas. And we operate on a cycle. And during the course of that cycle, we have some heat flow in here, and that heat flow in was in step 1. It was 842, so this is Q10, and it was 842.9 joules. And we are wanting to produce minus W, that's work out, work done on the surroundings. And indeed, we produced some. I go back and see what the hell we got. It was 107.2 joules. And that's less than the amount of heat we absorb to deal with. The system is back in its initial state, so what had to happen? We had to have some Q out, and we found that Q out. 735. Step 3 minus 735.7 joules. And remember I told you that people had trouble trying to take heat flow, which everybody knows that's energy, and you can run trains on it, and you can run steamboats on it, and you can generate electricity with it, you can do all sorts of things with it, but you pay a price. And we find out. I think that price is later we'll talk second law of thermodynamics, air price. So here we want to say what's the efficiency of Q to minus W conversion of this system run on a reversible cycle. And how would you define this efficiency? It's the total work out on the cycle divided by what?
Total heat out, or total heat.
Heat in. And so if we swap those numbers together, it's 107.2 divided by 842.9, and that turned out to be some little whoosy 12.7, or the efficiency in terms of percent is 12.7. This is not 0.127. So the efficiency is 12.7%. Not very high. What did I tell you they were laboring, probably getting back in the 19th century when this science was growing up? They were getting 5% of their life. This is a reversible process. It had no friction, no innings. That's all that dust piled up there was just pixie dust. The lines piled up. All right, so that sort of sets the stage for when we talk about heat to work converters using this second law, which will, I hope make a lot of sense. So I would just suggest to you that, an exercise is that you try one other cycle. Okay? Come down the same, that'd be the same isothermal. You come down this adiabatic, you stop, and the pressure is to, instead of going all the way down to here, you stop there. Then we go on this direction, that direction, and that direction. Have a different cycle. So what is this path here? This is isobaric what? What are we doing here?
Compressing?
We're not changing? No, we're not. Really, it looks like compression. It's really not. What we're trying to get, we're at the
Changing volume
300
to
Kelvin
constant
here,
pressure.
we're going down to this 200, we're cooling, isobaric cooling. We're restoring the energy to the gas that it dissipated in doing this work. And so consequently there is a work effect here. There's an area under that. We're going against it, going negative. Okay. And so we have the whatever that step is, cooling. C2 plus dW. See, now we do have a work term, so you have to add that in. The dQ is equal to NCD P, and dW is P2. This is B3. B3 minus D2. So you can do that. You can go around the loop and you can see. So another perfect thing. And just to give you a heads up on this pressure volume diagram, if you pick any point, we're talking about our gas now, let's still be our ideal gas. If you pick any point, you could start from there and go isothermally either direction, and you would be following a Boyle's law hyperbole. You pick another point, and you'd be on another Boyle's law, another Boyle's law, another Boyle's law, another Boyle's law, right? So you can just imagine this ensemble of curves there. But you pick any point, and you can go on a reversal adiabatic, and that goes down faster. And you can go from any point to any other point on reversible paths just by going up and down the route as necessary to get there. That turns out to be a wonderful opportunity, a wonderful heat to work converter. So we'll do that when we get there.
Yeah, it's just changing volume, but he wanted to tell you changing volume from V3 to V2.
I have a demonstration. I didn't bring it over. It takes me 4 minutes. Okay, I want you to see it, because without this and everything I'm going to talk about next few days, this is going to be gibberish. It usually is, but this will be even worse. Just take this up and then I go grab that. So we have the solution as n moles of A, VA So that is NA over NA plus NB times DA bar plus NB over NA plus NB times DB bar. And that, of course, is just a mole fraction of A times the partial mole volume of A plus the mole fraction of B times the partial mole volume of B. Now, in a binary solution, the mole fraction of A mole fraction of B is just 1 minus mole fraction of A. So we can combine like terms. We have VB bar plus XA times BA bar minus BB bar. All right. That's the equation that would fit any data we took on that binary solution. So suppose that XA goes from 0 to 1, or XB goes from 1 to 0. And if we've got water and alcohol, for example, we have molar volumes B1, 0, somewhere, and B2, 0, high ethanol and water. Now, if you made up mixtures of these and the solution was ideal, and some molecules were just as happy because the contentment they had in the solution was identical to the contentment they had in their own phase, this line would just be a straight line right through here. But in the real world, these things do goofy things. I'm just going to draw a casual curve here. Now suppose you want to know what is the partial molar volume. What are the partial molar volumes right here at this XA? Draw a tangent line and a curve there. The equation of this line is the volume of solution over volume of solution. Is equal to, we had it here on the previous page, is VB plus XA times VA minus VB. Straight line. Now that straight line has an intercept right here, which must be dV bar. One bar in this case. V1 plus X1. This must be partial volume of 2 over V. So if you imagine you go to the laboratory, you measure volumes, get that curve, and then you can draw tangent lines to it, and they will sweep out over here. They'll sweep out to the partial volumes. And that's what was done to get this. And they sweep out these fine curves for water and ethanol. But you see, there's a drop off. Partial volume is smaller than the molar volume, except for just a little bit right here. And that accounts for the shrinkage we saw in the tube. And next, just talk thermochemistry. We have the reaction A moles of A plus B moles of B plus whatever else is there. C moles of C plus D moles of D this is, when we come up with the equation, we have plus and minus here. Yes, okay. So what we do next is we see how we deal with this. How we account. So that's what I will do on my next